So when you see, for example, if you go in Alho Dam, when it's dry, you have all this cracking on the clays, and this space is because when the clay dries, it shrinks size. So it compacts and makes blocks like that. Yeah. So this is all due to this property that if water comes in here, in between the layers of this clay, it expands. And if the water goes out, it contracts. Yeah, so shrink swell clays. We talked about the type of charge that we have on the clays. Some clays will have only isomorphic substitution, some will have only pH dependent charge, and some will have both. Yeah. And the isomorphic substitution, we explained that there is when ion of lower valence substitutes ion of higher valence inside the structure of the clay, then it creates an imbalance of charge. And this charge must be compensated on the surface of the clay by an ion that is adsorbed. So this type of charges, they do not change if you change the pH. Yeah, let me move here for the part of the shrink swell clays, which is here. Yeah, this is the part that we did not show you last time. We stopped up to here, showing the properties of different clays. Here we see that if you have kyolinitic soil, when you add water, look at the level. This is dry. When you add water, look at the level of where the clay is. It's even lower because it settles, it compacts, yeah? It does not go up. But if you have multimorillonitic or smectite clays, yeah, this is dry, and when it's wet is higher because the clays expand. Yeah? So when it's dry, it's in this level. When it wets, it goes up. Kaolinite does the opposite. Yeah? It just settles more, but it does not expand. The water does not get in between the layers of the clays, and when it does not expand these layers, does not change the space in between these. So expansive clays are always 2-to-1 clays. Expansive clays are always 2-to-1 clays. So we talked about the types of charge, and we have the charges caused by isomorphic substitution, which are not dependent on pH, they are always there. And we have the charges which are pH dependent charge, which are linked to the hydroxyls on the structure. All the organic matter, all the iron and aluminum oxides, they have this type of charge. And the 2-to-1 clays and 1-to-1 clays, the aluminum silicates, they will have both. Yeah, they will have a little bit of this pH dependent, but also a lot of the isomorphic substitution permanent charge. And here are, so just for comparison, this is no need for memorizing. The information here is 2-to-1 clays have much more charge than the 1-to-1 clay, kaolinite, yeah, and allophonimogolite, which are volcanic clays, have much more charge also than those. Yeah, these are amorphous clays. And humus, which is organic matter, will also have a lot more charge than all of those. Yeah, so organic matter is the type of colloids which provide more charge in the soil. So this is the information you need to remember from here, is that different types of clays will provide different amount of charge into the soil system. But what is so great about having charge in the soil? Why do we care about charge? Why is charge important? Why do we want the soil to have charge?
Because maybe it would attract the elements to the soil.
Yeah. And what happens if you do not attract those elements?
The soil will be poor, does not have enough nutrition for plant to grow.
Yes, so we care that basically it retains the nutrients for the plants. Yeah. So the plants will absorb nutrients only on their ionic state. Only in the ionic state. Ammonium is a cation, yeah? Nitrate, anion. Phosphate, an anion. Sulfate, anion. All the forms that the plants absorb in the soil, they are ions, and they are present in the soil solution. Never the plant will uptake something from the solid phase directly. Always have to move to the soil solution and then from the soil solution into the root. And always to get inside the plant, it has to be in the ionic state. So if you need ions in the soil, you need something to hold those ions. So you need some particles who have charge on their surface, so those ions will be retained. And what happens if you don't have those is easily, if water moves, all the ions go with the water. If you have the charge, the water moves, the ion stays behind in the soil. So leaching is the removal of these ions by the movement of water. So if you do irrigation, if there is rainfall, and if you only have sand on the soil, no clays, no organic matter, all the nutrients from the plants will go in the water. Nothing will stay behind for the plants. So you need the charge in the soil to be able to retain the nutrients for the plants, the nutrients for our plants. So because the clays are negatively charged in general, you remember even that the pH dependent charge, the soils will usually be in pHs over the isoelectric point. So the net charge will be always negative. Maybe more negative charges are created, less negative charges are created depending on the pH. But in soil conditions, you will get negative charge even from pH dependent charge. There is some positive charge in the soil also. There is an anion exchange capacity. But in general, the majority of the charge of the soil is negative. So being negative charge, it's attracting cations, positively charged ions. Now, what happens if you have an anion? Do you have no retention capacity in the soil? Let's say if you have a phosphate. What do you guess? Phosphate will be repelled from the soil and will just leach, or there is any retention capacity for anions? You have cation exchange capacity, which is the capacity of the soil of retaining those cations. The cations are attracted to the negative charge in the soil. Soils are negatively charged on the surface. Cations will be attracted there. What happens if you have an anion? Will be repelled only?
It will stay.
Yeah.
It will
So-
be in that covalent bond.
Could be. Yeah. Now the chemistry of different anions will be different. Some of them, yes, they will be only repelled and they will not be retained with high energy in the soil. For example, nitrate. They have low affinity, but some other anions, they have the ability of even forming some other ions that they, for example, phosphate will form calcium phosphate, for example. And this calcium phosphate will act as it was a cation. So it will be still attracted to the surface through the bridging of some cations. So if you have polyvalent cations in the solution, like calcium, magnesium, for example, aluminum, iron, then these polyvalent cations will act as a bridge between some anions and the surface of the clays. So let me repeat that. Polyvalent cations, they have more than one charge. You remember that they are mediating even the flocculation of these clays, the formation of soil structure. Polyvalent cations are bridging different things that are negatively charged together. If a calcium has two positive charge, one positive charge can satisfy one clay and another clay. But also it could be that is linking one anion with the surface of the clay. So it happens that the more polyvalent cations you have on the solution, also the cation exchange capacity will also retain some of the anions in the double layer of adsorption. So this adsorption surface, it does not consist in only one monolayer of ions. There is a cloud of ions which equilibrate themselves, especially if you have polyvalent ions. If these ions have more than one charge, they will only not be satisfied with one charge, but they will make that these are creating layers and layers of adsorption. Okay, so cation exchange capacity holds nutrients, not only cations, but also to some amount some anions, yeah? Some anions are also being held by the cation exchange capacity. But because the surface of the clays are negatively charged, we are representing this charge as cation exchange capacity, yeah? The cation exchange capacity is the sum of all the charge you have in the soil. If you have 1 gram of soil, how many adsorption sites do you have there? If you sum up all those charges, this is the measurement of the cation exchange capacity. Yeah? Clear? How do we know that? How do we measure? Yeah? So let me go first for how do we measure. This farther away down here. How do we measure that? We can measure that by saturating the soil. Did you do that on the lab? Cation exchange capacity? So you tell me, how do you measure?
We make saturated base,
Yeah?
and then we use the panel to extract the solution.
Yeah?
And after that, we use the pH and the EC devices to measure how much the pH and the count is.
Yeah, there's ECPH, but not the cation exchange capacity. A cation exchange capacity is a different protocol for that. Normally, to measure that, you saturate the soil with a given ion. Yeah? In this case here, showing you put an ammonium solution. And the ammonium will displace all the other ions. You saturate the soil with only ammonium. Now you can now wash with water. Excess of ammonium will go out. Yeah? The excess of ammonium will go out. The only amount of ammonium that's staying on the soil is the ammonium that is retained by the charge in the soil. Okay? Now you can add another ion in a saturated form. Now the solution is not saturated with ammonium anymore. The only amount of ammonium that is there is the one that is bound to the colloids. If you add a potassium solution at a very high concentration, that potassium will displace the ammonium from the soil into the leachate. So you wash your soil with a saturated potassium solution, then the potassium will displace the ammonium will go to the solution here. Now if you quantify how much ammonium you have here, it's exactly the same amount of charges you have in the soil. If you wash your solution and remove all the ammonium that was adsorbed, if you consider that was only ammonium here, all the ammonium was coming down. If you quantify how much was the ammonium here, you have all the charge that was there. Yeah? And then you can divide that amount of charge by the weight of the soil, then you have the amount of charge per weight. So this is the way you quantify cation exchange capacity. But keep in mind, even though you're quantifying ions, the measurement is the amount of charge you have on the soil. Yeah? Cation exchange capacity is the amount of charge that you have on the soil. There is another thing that we have to consider. When you have complex systems in the soil that you have multiple ions, some will be ammonium, some will be potassium, some will be calcium, even hydrogen, sodium, all the cations are there. Which one will have preference for the solid phase? Which one will be occupying the charge in the soil and which one will be in the solution? Yeah? There is an exchange between these ions, between the surface of the colloids and the soil solution. Some of them will have preference, okay? And this preference, this strength of adsorption is related to the charge density, okay? Charge density means by the size of the ion, how many valence does it has? Let me repeat. If you have a small ion with one valence, like hydrogen, you can have more charge density than a big ion with two valence, like calcium, for example. Calcium will be a big ion and has +2, and you have a small ion like hydrogen with 1+, but in the same space you can fit more charge. In the same space you have one calcium, you can fit many hydrogen. then you can build up more charge. The density of charge for hydrogen is higher than the density of charge for calcium. The more the charge density, the higher the affinity it has for the solid phase. Is it clear, this concept? So hydrated radius, it's one of the things that you have to consider. It means what is the size, what's the radius of that ion, and the valence, how many charge does it carry. If you divide one thing by the other, you get charge density, the amount of charge for a given amount of space that you have. So smaller hydrated radius means and greater valence means they are closely attracted, more strongly attracted to the surface. So you can order these ions by charge density. The ones that have more charge density has higher affinity, and the ones that have lower charge density will have less affinity. And if you order this, you get this, which is called the lyotropic series. The lyotropic series means when these ions are organized by how attracted they are for the soils, for the surface of the clay. Hydrogen is the one with the highest, with the strength of adsorption. Sodium and potassium are the ones with lowest strength of the adsorption. And this is in order: aluminum, calcium, magnesium, ammonium, and so on and so forth. Okay? So it means this, that if you have sodium, potassium in the solid phase, as long as you get any of this in the solution, it will go to the solid phase, and the sodium and the potassium will go to the solution. Easily you can displace these ones. To displace these ones, you need high concentration of the other ones. There is a function of the affinity, but also a function of the concentration. So if you have high concentration of the low affinity, still you can displace the low concentration of the high affinity. But even with low concentration of the high affinity ones, you can displace the ones with low affinity. So the ones with high affinity will have preference for the solid phase. This is called the lyotropic series. Is that clear, this one? This will be on the exam for sure. Go ahead.
The ammonium is equal to potassium, but
higher than sodium. So they have low affinity, all of them.
But the last example showed that the potassium display ammonium.
Yeah, but how do you do that? You just increase the concentration of potassium. You do the potassium, let's say 5 molar concentration of potassium, whereas the only ammonium that you have left on the soil are the ones satisfying the charge. So even in the solution, you will not have a lot of ammonia, almost no ammonium in the solution. So it will be a saturated concentration of potassium. Therefore, by sheer the pressure of having high concentration in the solution, it will displace the ammonium from the solid phase. So first you saturate your soil with ammonium, then you wash your soil with water without any ions on it, so it will remove the ammonium from the solution. The ammonium that is on the solution on the soil will go away. Then the only ammonium left is the one in the charge of the clays. Then you add the solution of potassium with high concentration. Just because you have more concentration here, they are equal here. No? You can see they are equal in their strength of adsorption. But if you have one that is with very high concentration, it will, by sheer difference in concentration, it will displace the other one. The concentration acts like a sort of pressure. There is and the affinity acts like regulating the. So it's a little bit outside the scope of this lecture, but you have rate constant of adsorption and rate constant of desorption. So the speed and the energy in which these ions are attracted to the solid phase is regulated by the charge density. Is it clear? Or?
Yes.
Okay. So, okay, we already talked about this part. So cation exchange capacity is the sum of all exchangeable cations in the soil, but actually it's a measurement of all the charge, the charge that you have in the soil. The units centimoles of unbalanced charge, centimoles. So it's just a way of normalizing that if you have some ions that had more than one valence and you're counting the ions, you should not be counting by the number of ions, but the number of charge that you can absorb. So if you have calcium, that will make for 2 moles of charge. Yeah. If you have calcium in the place of a monovalent cation like potassium, the calcium, because it's +2, it will count double because there's you actually here you're counting the charge on the surface of the clays.
This equation is important to memorize it.
Yes, what's important for you to memorize is the concept of cation exchange capacity is measuring the amount of charge you have on the soil. Yeah. So it means that if you have polyvalent cations, these are satisfying more than one charge. Yeah? If you have +2, +3, +4, these are occupying more than one adsorption sites in the surface. Yeah. So it actually is a directly measurement. If Cc is 10 centimoles per kilogram, it means that it can absorb 10 centimoles of hydrogen. It's a direct measurement of, if you have a monovalent cation like this, like hydrogen or potassium or sodium, the Cc will be a direct measurement of how much of that can the soil hold. Now if it was calcium here, it would be half of this. See, because calcium is +2. So if it was calcium, it would be 5 centimoles of calcium. You see, calcium has 2, valence 2, so it means that the amount of charge in the soil is not the amount of ions, any ions, is the amount of charge. Is the concept clear? You're measuring how much charge the soil has, and depending on the ion, that will be more ions or less ions, because of the valence of those ions.
Here in the 5, in the calcium,
Yeah?
it have positive charge at 2.
Yeah.
Why it's 5 and the calcium 1?
These centimoles of charge per kilogram is the amount of charge you have on the soil. If you have the opposite of hydrogen, 10 centimoles of hydrogen will have 10 centimoles of charge. Yeah? But 5 centimoles of calcium will have the 10 centimoles of charge because it has 2 valence.
It's an independent charge.
The moles of an ion is the concentration of that element. It's the amount of elements that you have in the solution.
That's mean it's 5 in energy horizon.
Yeah. So it just to say that when you measure cation exchange capacity, you're measuring how much charge you have on the surface. The amount of ions that can retain actually depends on how much is the valence of that ion. If you have more valence, you have less absorption of that ion because the same ion will satisfy more than one charge in the surface of the clay. Does that make sense for you? Yeah. So no calculations needed, just to understand the principle. Yeah. I will not ask you for calculations about this. If you understand the principle, that is enough. And if you don't understand the principle, now it's the time to ask. I will explain more. Okay?
For example, if we compare it between aluminum and hydrogen,
Yeah.
and the amount of CEC on the on the hydrogen is bigger, greater than the aluminum. That's
The Cc is a property of the soil. Yeah. Cc is a property of the soil. It does the Cc, cation exchange capacity, is a property of the soil. It's not about the type of ion that you are absorbing. The same amount of Cc will absorb more of one type of ion and less of another type of ion. The Cc is about the type of clays and colloids that you have on the soil. Some clays will have more charge, some clays will have less charge. And the more clays you have, the more charge you will have. Okay? The more organic matter you have, the more charge you will have. Cc is a measurement of how much charge you have on the soil. Now this charge can absorb ions. Yeah? There's a capacity of this charge to absorb ions. How much of ions will you absorb? Depends on the valence of those ions. If you have 2 valence, there's certain amount. If one valence, there is another amount. If valence is 3, even less. You see? So it will balance out. You have certain amount of negative charge, you have the same amount of positive charge that will absorb. And depending on the ion, you have more positive charge for the same amount, for the same molecule. The same molecule of the ion will carry more charge than the other one. But this is a property of the soil. You're not measuring this as a property of the ions in the solution. Yeah, this is a property of the solid phase, of the soil solids. Is it clear? It's a property of the soil solids. It's not the number of ions, yeah? Not the number of ions, it's the amount of charge you have on the soil. Clear this one? Exam question, eh? This will be in this exam for sure. Exchange affinity, we already spoke about this, yeah?
Yes.
So CEC depends on amount of clays and types of clays. Some clays will have more charge than the other clays. Organic matter will have more charge than 2-to-1 clays. 2-to-1 clays will have more charge than 1-to-1 clays. And the amount of these clays. If you have 2% clays, you carry that amount of charge. If you have 10% clays, you have much more. Yeah. So the amount of clays will define what is the amount of charge. So as a rule of thumb, you can roughly estimate your cation exchange capacity based on organic matter and clay content. So organic matter times 200 plus clay times 50. So it's averaging, assuming that the type of clay you have has 50. If you have the percentage of that clay, multiply by 50 and organic matter by 200. But organic matter can go up to 600, 800, depending on how humidified it is. And clays could be as low as 10 up to 200, but you say like a rough estimation, you can calculate by using this formula, just to know around how much you have. So you want clays on your soil, you want organic matter on your soil for the chemical properties. The more you have organic matter, the more clays you have more cation retention. It just so happens that clays, if you have too much, it will be bad for the water movement on the soil. It will be very heavy soils, difficult to handle from an irrigation point of view and water management point of view. But organic matter, there's no limit for that. You can have 50% organic matter, it will be a great soil for you. The more organic matter you have, it will not mess up with other properties. Clays, you can only have so much that will still be a good soil. If you have 5-10% clays, very good. But if you have 20-30% clays, it's becoming very heavy. It's a soil which is a problematic soil. It's a clay soil, okay? Base saturation is another concept related to soil chemistry. We were talking about all those cations, but different cations, they have different properties based on the reaction they have. Some of the cations will have acid reaction, some will have alkaline reaction. It means that if they are in the solid phase, when they come into the solution, they will make the solution more alkaline or they will make the solution more acid. The ones that make the solution alkaline, they are called bases. Yeah? What is the percentage of the cation exchange capacity which is occupied by bases? It's called base saturation. It means these are the cations that have alkaline reaction. Divide them by the cation exchange capacity, multiply by 100, you get the percentage of bases on your soil. If you have pH 7, 7.5, you will have around 80%, roughly 80% bases on your soil. When you reach 8, you will have here like 100%. When you reach pH that are alkaline 8.5, this will approach to 100%. And in acid soils, this can come as low as 50, 40% if you increase the acidity. Yeah? You will notice here what are the ions that are not present here. What cations are not present here? Yeah? For example, here you have hydrogen and you have aluminum, and there's another one that's not mentioned here, iron. Yeah? Iron, aluminum, and hydrogen, they are acid cations. Means when they come into the solution, they decrease the pH, they increase the acidity. The other ones, when they come in the solution, they alkalinize the solution. Yeah? They're bases. Do we have the explanation of here? This is the explanation of why they are bases. This is a little bit displaced, but this explanation of what they are, why they are acid cations, and why they are basic cations. Yeah, base saturation is the percentage of basic cations. You have more or less percentage of saturation of these basic cations. Consider that my hand here is the clay surface. Yeah, the ion with highest affinity for the clay is a hydrogen. When you go, if there's a calcium here, the calcium goes for the solution, hydrogen takes its place from the solution. It means there is less hydrogen on the solution. Less hydrogen, more alkalinity. It's a base, okay? That happens with any cation except for iron, aluminum, and hydrogen. What happens with iron, aluminum, and hydrogen? Hydrogen is the obvious one. If there is hydrogen on the solid phase, here's the clay, you have hydrogen adsorbed. If hydrogen goes into the solution, the pH of the solution goes down. It's the acidification, because pH is the measurement of hydrogen. The concentration of hydrogen is pH. You remember the concept of pH, no? pH is a measurement of the inverse logarithm of the concentration of hydrogen. Yeah, it means that it moves. We will talk about pH in a little bit. But pH is, if pH goes down, there's more hydrogen. If pH goes up, there's less hydrogen. So if hydrogen is on the solid phase, if hydrogen is in the clay, if it desorbs and goes to the solution pH will go down because there's more hydrogen. Now what happens with iron and aluminum is iron and aluminum forms hydroxides. Do I have it here maybe? Yeah, this is the reaction of calcium. Here, aluminum and iron, they form hydroxides. They take the hydroxyls from the solution. Water dissociates in a proton, hydrogen, and a hydroxyl, OH. If the aluminum makes a hydroxide here, there is more hydrogen in the solution. It takes the hydroxyl and therefore increases the concentration of hydrogen. So this is an acid cation. The two cations that make this happen is aluminum and iron. So if there is aluminum on the solid phase, when aluminum goes to the solution, there is more hydrogen. If iron goes from the solid phase into the solution, there is more hydrogen because they make these hydroxides. Okay? So acid cations, aluminum, iron, and hydrogen. All the rest are bases. Base saturation is the percentage of bases you have on the soil. What is the percentage of all the ions that are not iron, aluminum, and hydrogen? If you add them up, all the ions, the cations that are not aluminum, iron, and hydrogen, you divide by the total amount of charge that you have on the soil, you get how much you have of these ions. The maximum you can get is 100%. It means you have no hydrogen, no aluminum, and no iron. And that can happen if the pH is very alkaline. If the pH is very alkaline, you can have that all your solid phase is occupied by bases. Yeah? All the solid phase occupied by bases. In Oman, in high salinity, you can reach that, 100% base saturation. If you have low salinity, it will not happen. Always this will be something like 80, 90% or something like that. But with high salinity, you get accumulation of bases in the soil, and this can reach even 100%. So we talked about aluminum silicates in the soil, but there are other types of colloids. Hydroxides are some of them. Yeah, you said aluminum and iron hydroxides. We just mentioned now before that when iron and aluminum goes to the solution, they can form hydroxides. So they form like a secondary type of mineral that is part of the solid phase of the soil. And these also have colloidal properties. Yeah, they also have colloidal properties. Organic matter, humified organic matter also, we already mentioned on that table that they have the highest amount of charge in the soil is on the organic matter. Mostly negatively charged, some of them will have positive charge also. How much do you guess its organic matter concentration in Oman?
0.6.
0.6 is a good estimation. Yeah, below 1% usually. If you have soils which are constantly being amended by manures and compost, then you can reach 2-3%. But because of the climate in Oman, it's very hard for you to increase the organic matter. The climate is so hot that the decomposition rate is very high. So the more you add also, the more you lose, it becomes CO2. The microbes eat the organic matter and decompose the organic matter. So you can never reach that much of organic matter here. In temperate climates where it's colder, you can reach up to 15-20%. In Chile, you have 20-25% sometimes of organic matter in the soil, which makes it more fertile. It's a better soil for crops. But here you cannot do it because the climate is hot, so the microbes will decompose this organic matter very quickly. Yeah? So these amorphous types of materials, when they decompose to the fullest and stabilize in soil, they're called humus. Humus is a term that in science we are ditching. Nobody's using that anymore. It's this, old style, because this is based on what is left behind after the alkaline extraction and the acid extraction. But this is not the best way anymore for characterizing this organic matter. Yeah? All the charge is pH dependent, mostly negative charge, and it's completely amorphous. There's no structure that you can say humus will be that structure. It's every molecule will be different from each other. Yeah? But it's just organic molecule that was, the microbes took all they could, and the things that they could not eat is left behind, and this is the humus. Yeah? The product of the decomposition of organic matter in the soil is humus. It's not the molecule that was part of the plant anymore. It's modified chemically. This molecule now is chemically different from any molecule you will find inside the plant. It's not that this was a lignin and now the lignin stayed behind in the soil and you can say, okay, this is lignin. Lignin is one of the things that form humus, but the humus in the soil will be chemically different. Yeah? It's chewed up by the microbes. Enzymes attack this in all ways possible, and this is what's left behind. Again, organic colloids have pH dependent charge. Yeah? The same explanation we gave for pH dependent charge in aluminum silicates holds here. If you increase the pH, you get more negative charge in the humus. But what is pH? We were talking about this just now.
Dependent H.
The concentration of hydrogen. Yeah? But it's a weird way of measuring it. Yeah? It's a minus log of the molar concentration of H+. You remember that from high school chemistry? pH, the minus logarithm. It means that if you have pH 7, what does it mean? What is the concentration of hydrogen? 10 to the minus 7. It means 1 over 10 million. This is moles of hydrogen. You feel that? The concentration of hydrogen is the minus the logarithm of the concentration of the H+. So the concentration of H+ is 10 to the negative power of the pH. just by working out the logarithm, the inverse of the logarithm. So if you have pH 6, 1 over 10 million. Yeah. Even if I can raise here a little bit or do I have a marker? Anyway, you follow, this is from high school. Yeah, I don't need to explain this too much for you, but always keep in mind that every point of pH, you are changing 10 times the concentration of hydrogen. If you move from 6 to 7, you have 10 times less hydrogen. Now if I move from 6 to 8,
1,000.
100 times less. From 8 to 6, 100 times more. If I move from 10 to 7,
1,000. 1,000.
1,000 times more hydrogen. From 10 to 7. In 7, you have 1,000 times more hydrogen than at 10. It's an inverse logarithm relationship. And every point of pH is 10-folds the concentration. pH is a master variable for soil. In fertility, in microbiology, and anything you do in the soil, pH is hugely, hugely important. Why? Why do we care so much about pH? Why do we care about pH?
Because the amount of hydrogen, it's maybe to change something in the organic matter and it's independent on the water going inside with the action.
Yeah, it conditions all the chemical reactions in the soil. The chemical reactions in the soil are regulated by pH. Basically, one of the main things that you will find is that many ions in the soil, they are soluble in one range of pH. They are not soluble in acid pH, they are soluble in alkaline, or the opposite. Some are soluble in acid conditions, some are soluble in alkaline, maybe they are soluble only on the neutral side of the pH, because they interact with each other differently depending on the pH concentration. So it means that if you want to keep those ions soluble and make them available for plants and microbes, you need to have the solution of the pH in the soil at the pH where those ions are available. If you change the pH, you change the availability because they precipitate. For example, you form calcium phosphate at alkaline pHs. Yeah? Calcium phosphate is formed in alkaline pHs. In acid pHs, calcium phosphate is soluble. At acid pH, aluminium phosphate is precipitated. So, in alkaline pHs, you solubilize it. So, depending on what you have, sorry, if the plants need the phosphorus and the calcium, and if you have very high pHs, the phosphorus and the calcium, they are locked into each other. They are precipitated. If you acidify, they can come into solution in their constituent ions. They can dissolve. So pH regulates those reactions in the soil. Not only that, you remember that hydrogen is the one with highest affinity for the solid phase. So also hydrogen will desorb some of those cations for the solution. Sorption, desorption is regulated by pH. The more hydrogen, the more you displace some of those ions into the solution so the plants can take it. So chemical reactions in the soil are strongly regulated by pH, and that regulates nutrient availability and availability of any element in the soil. It regulates all chemical reactions, okay? So this is why we care so much about pH. Already we explained that acid cations and basic cations in the solid phase, they regulate the pH. So that's the reason we have buffering. Have you heard about that word, buffering? In the lab you use some buffers sometimes, solution buffers. What is a buffer? Maintain the pH, yeah? It resists the changes in pH. You know, pH buffer, it means if you change concentration of some ions, the pH in the solution will be about the same, yeah? The buffering capacity in the soil in the solution is based on a combination of a base and a weak acid. Yeah? In solution, a buffer is a combination of a base and a weak acid, but in soil is based on what type of ions are in the solid phase. If you have acid cations on the solid phase and you're changing the pH, it means you are making this come into the solution and they will keep acidifying the solution. So it means if you have these, this means you have reserve acidity. It means your soil is storing acidity on the solid phase. And every time you change the solution, you alkalinize the solution, the solid phase will desorb some of the acid cations and buffer the solution back into the same pH. And in the case of Oman, you will have bases. Yeah? And every time you try to put some more hydrogen in the solution, acidify, the hydrogen will go to the solid phase, and this will come into the solution, and therefore there's a capacity of a soil of buffering the solution, resisting the change of pH. So the buffering capacity of the soil is the amount of ions and the type of ions that are in the solid phase are resisting the change of pH in the solution. When you acidify the solution, the solid phase will desorb some of ions, and these ions will keep the solution pH in what it was before, roughly. The more cation exchange capacity, the more the capacity of buffering the soil has. This is very important. Why? Imagine that pH is going up and down like this, like crazy on the soil. If it becomes too acid, will kill the plants, will kill the microbes. If it becomes too alkaline, will kill the plants or kill the microbes. But because you have this buffering capacity, now it's roughly stable. Yeah? And this stability of pH will make a stable environment for plants and microbes. Therefore, living beings can thrive in those conditions. Yeah? If you have something that is sulfur oxidation and that the pH goes down like pH 2, immediately the solid phase will desorb some bases and therefore equilibrate that and regulate the pH up. So it will create a stability, and this stability is important for sustaining life. Yeah, for sustaining life. So this is the reaction of base forming cations, formation of carbonates and bicarbonates in the soil also, all have this balance of hydroxyls in the soil, where acid cations will have the balance of protons on the solution, and therefore they have an acid reaction. Acid cations will have a reaction when they desorb, they form hydroxides and they release some hydrogen. You know, this is the last slide. It's just to show some of the nutrients, important elements we have in the soil, and we have the solubility range they have. Some of them are not soluble or not available in acid pHs. Some of them will be low availability in very alkaline pHs. So what you're looking at for fertility, for the ability of soils of sustaining plants, you need to keep a roughly neutral pH. The ideal pH is between 6.5 and 7. Yeah? 6.5 is the sweet spot. In Oman, they will always be towards the alkaline condition. So you will see here, some of these ions, especially iron and manganese, will be deficient. So you have always to be worried about the fertility of iron in alkaline soils. Calcium also can be, depending on the other type of counter ions, can form a lot of precipitates in alkaline conditions. But you have a lot of calcium in Oman, so usually you're not so concerned about calcium. But in extreme conditions, even the calcium can be deficient because they precipitate. Yeah? So this is why you care so much about pH. The sweet spot are about 6.5 up to 7. And if you alkalinize or acidify, you lose availability of nutrients for plants because of precipitation reactions. That was all for soil chemistry. Questions?